Yeah.
Yeah.
Hello everyone. It's our pleasure to have like Weijie here to share about his recent work about the quantum extreme learning machines, and in this paper it basically studies different kind of aspects of the machines, like for example expressivity and trainability. I guess like you guys are not studying the generalization abilities, right? So mostly on expressivity and trainability. So I guess like Vijay will be able to tell us more about that. Yeah, Vijay, the floor is yours.
Cool. Thank you. It's a great pleasure to share our work here. Uh, Feel free to interrupt me at any point if you got confusing or want to discuss. So yeah. Okay, let me turn on the laser point. Yeah. First, I would like to thank my collaborators, Joshua and Merhat, also from EPFL, Owen from Oxford, and our supervisors, Superlat, uh, uh, who is a alumni from CQT and will become a professor in Thailand, and Tip from Chula in Bangkok, as well as Zoe. So let's start with the framework of classical extreme learning machines. Basically, they consist of three parts: the input layer, the hidden layer, and the output layer. The core idea of extreme learning machine is that the training concept is super simple. Basically, it's only a single layer of linear regression between hidden layer and output layer. And the parameters of uh, this map between input layer and hidden layer are fixed. So they are kind of hyperparameter. Then the optimization is just a convex optimization problem. The training is super efficient and the trainability is also guaranteed. The quantum version, the QELM, use a quantum substrate to replace this map between input layer and hidden layer. Yeah, also with data embedding and measurement. Due to rich dynamics of quantum system, people expect that the QELM can achieve a higher predictive power with relatively low resource requirement. In this work, we consider a reservoir consisting of two types of qubits. One type is accessible qubits. On those we can encode data. Another type is hidden qubits. On those we will not encode data. So this distinction is motivated by their different roles. So we will see that the number of accessible qubits NA will significantly affect the performance of QELM, while NH can be considered as a hyperparameter. Yeah, so basically NH, we will say that it will probably affect the inductive bias of this system. So after we define the framework of QELM, we draw the circuit diagram, and we can write down the state of system after each step. So first, the initial state of accessible qubits is denoted as 0, 0, and rho x is the state after data encoding. Then the state of the composite system, rho x turns out by 0 state of hidden qubits will evolve under the dynamics of the reservoir UR. Then we obtain M measurement outcomes, M classical outcomes from M observables. Then in the end, the optimization is just a linear regression on these M classical values, similar to the classical case. So I want to remark that here, in contrast to the hidden qubits, we just assume the initial state is 0. For classical qubits, we denoted it as 0, 0 because we will choose the eigenbasis of encodings generator as the computational basis. So in summary, we have kind of 4 motivations to study QELM. First, it's a machine learning model can provide easy trainability. Second, compared with parameterized quantum circuits, the QELM is not parameterized. The quantum part is not parameterized. So QELM can avoid the issue of baryon platters. Another feature map is another feature of QELM is the complex feature map due to quantum dynamics. And finally, it's also a motivation for us because we are super interested in quantum reservoir computing. So quantum reservoir computing is a kind of multi-step version of QELM, or maybe I should say that QELM is a simplified version of quantum reservoir computing, which only have 1 layer. So in general, QRC will reinitialize the accessible space and upload the data corresponding to the next time point on accessible qubits, and then evolve the system again. So if we understand the QELM, then maybe we can extend the results to QRC, and this is our ongoing project. Okay, let me review the previous work on QELM. So first, the paper by Luca Innocenti studied the QELM with quantum data. They studied the expressivity of QELM and the controllability of trainable parameters. So the controllability means that in the training stage of QELM, we will tune the weight to fix the label. So the trainability means that, the controllability means that what can be controlled when we tune this trainable weight. And there are 2 works studied the universality of this learning model, and along with many case studies using classical benchmarking datasets. So they compare the performance of quantum extreme learning machine with classical extreme learning machine, as well as other learning models.
Sorry, I have a question over here.
Yeah.
So so in this works, right, their circuit structure is it exactly the same as the one that you consider in this in your work? Like so the settings for the circuit itself, is it similar to the one that you considered in your paper?
Do you mean this paper or these 2?
Yeah, this paper. Yeah. So what are the the setting in terms of like what so like do you guys each of this paper like is their definition on quantum extreme learn like machine similar? And then I know like quantum extreme learning just means that you kind of initialize some substrate and then just like measure it and do some linear feature like linear regression on that, right? But in terms of the circuit structures that you guys have kind of proper definitions across all the papers, or each of these papers has their own kind of initialization. Do you get my what I mean?
So basically, these 2 papers they didn't exactly consider this extreme learning machine, but we think that our framework, the QELM, can be considered as a type of these frameworks. Does this answer your question?
So it's like your setting is kind of captures all the previous the structure the circuit structures of this previous work. Am I understanding correctly?
I would say this work capture our framework.
Oh, okay. I see.
Yeah. So then we think that their result on universality can also transfer to QELM framework.
I see. Okay. Okay.
Yeah. Okay. So yeah. Basically, the potential of quantum extreme learning machines for classical data has never been studied in detail. And in our work, we decompose the prediction of QELM into Fourier series. Basically, it's inspired by the pioneering work by Maria Schwartz about the Fourier decomposition. And based on this expression, we discuss its expressivity and controllability. Remember, I mentioned that the controllability is like what can be controlled by tuning the trainable weights. And in case of Fourier theory, because the linear regression is a kind of so the linear regression on Fourier series is also linear. The linear combination of Fourier series is also Fourier series. So the controllability can be transferred to the controllability of Fourier coefficients. Namely, when we tune the trainable weights, how can we control the Fourier coefficients? Besides from this, we also study the simulability of QELM, as well as its limitation in scalability, the exponential concentration. So yeah, the starting point of our analysis is to derive such a Fourier series for QELMs. So we assume that the embedding takes this form, and we call H the generator of this embedding. Then we choose the eigenbasis of this generator, such that H and U are diagonal in this basis. Then the measurement outcome of any Hermitian observable can be expressed as a Fourier series. The achievable frequencies is determined by the differences of eigenvalues of this generator, or simply we say that the frequency is fully controlled by the encoding strategy. But the coefficients are determined by both reservoir, UR, and the measurement.
Sorry, like just to clarify a bit, like for the measurements, do you measure the hidden qubit as well, or only on the accessible qubit?
Yeah. So at this step, OK is a general observable on the composite space. But later on, when we do the numerics, we limited it to accessible space.
I see. Okay.
Yeah. More specifically, we will limit it to local measurement.
Okay.
Yeah. And in the concentration part, we will see that the global measurement is also a source of concentration.
Mm-hmm.
Yeah. Okay. So remember that the output of QELM is a linear combination of measurement outcomes. So yeah, it can be written as a Fourier series with different Fourier coefficient, and this coefficient is a linear combination of the coefficient of observables expectation values with a trainable weight eta. So we know that the Fourier modes, like they are orthogonal to each other. So the number of Fourier coefficients can be considered as a kind of a measure for the expressivity. But remember that we can only control eta instead of b omega. So it doesn't mean we can control all the Fourier coefficients. Motivated by this, we define the expressivity of QELM as the cardinality of a small set, such that its element can such that we can use its element to reconstruct any expressible function of this QELM. So yeah, the expressible targets is a set where the vector, the trainable weights, is an arbitrary real number. So intuitively, we can say that this Fourier expressivity consider not only the number of achievable frequencies, but also the correlation between the Fourier coefficients, or we say the degree of freedom of these Fourier coefficients. So let's upper bound this expressivity. First, the Fourier single modes are naturally orthogonal functions. Consequently, f is smaller than the number of Fourier frequencies. This is further upper bounded by the number of eigenvalues, by the number of differences of eigenvalues 4 to the NA. Because the dimension is 2 to the NA, then maximally we have 4 to the NA distinct differences. Another upper bound is given by the number of observables, because the prediction is a linear combination of these measurement outcomes. So yeah, another upper bound is M, capital M, the number of observables. The third upper bound is induced by the locality of measurement. Intuitively, if you measure, let's say 100 observables on only one qubit, you cannot obtain more information than just perform a minimal information completed QELM with the size 4 to the NO. NO is the number of qubits we measured. So yeah. Or formally speaking, the ICPOVM spans the space of CF adjoint operators. So any observable can be expressed as a linear combination of the elements of a ICPOVM set. And here, the Fourier coefficient, we say that is additive in this observable OK. So the expressivity is always less than 4 to the NO. Now we look into details of this upper bound. So first we consider the specific cases for the upper bound induced by a number of frequencies. So we know that the achievable frequencies are fully determined by the encoding concept. And here we discuss some common encoding. The first type is Pauli reuploading. So basically, we consider this type as a general class of data uploading. We assume that the encoding unitary is separable. It's a tensor product of single qubit rotation gates. But the key of Pauli reuploading is that the generator for each qubit is the same. Consequently, the frequency spectrum of this whole unitary is equidistant, and you will only get polynomially many frequencies. But if you scale your generator with a parameter beta k, k denotes the index of the qubit, and beta k is exponential in this index, then thanks to this parameter, you will get different spacing between the eigenvalues of each generator. So in the end, you can get exponentially many frequencies. So I want to remark that this number of frequencies, 3 to the NA, so you will always get 3 to the NA as long as your generator has a symmetric spectrum. So namely, you will have a lot of redundancy for the eigenvalues differences equals to 0. However, I think there's a very recent paper reviewed many different encoding strategies and their resulted frequencies. So there is a special encoding concept that can provide you the tight upper bound of the number of frequencies, namely can provide you 4 to the NA of frequencies. I forgot the name of that encoding concept, but I will put it here and maybe share the slides with you later. So now we look at another two upper bound. So another two upper bounds are all about measurement, the number of measurement and the locality of measurement. We assume that M is polynomially in system size. So this upper bound is always tighter than this. And for the following, we just consider these two upper bounds. By comparing M and the cardinality of omega, we distinguish two regimes. If you have more observables than the number of frequencies, then you can fully control all the single Fourier modes. And we call this regime the full control regime. The Pauli uploading, which will provide you polynomially many frequencies, can belongs to this regime. But since the number of frequencies is polynomially many in system size, we will see that this can be classically surrogated. If the number of observables is smaller than the number of frequencies, we call this regime the partial control regime. And in particular, the exponential encoding, which will provide you exponentially many frequencies, belongs to this regime. Basically, when you choose exponential encoding, you will extend this gray area indicating the space spanned by these Fourier modes. So probably for some targets, you can expect some potential quantum advantage, but we don't know yet. We don't know which are those targets. Yeah, so far we discussed the encoding and measurement. We see that they will directly affect the Fourier expressivity. But how about the role of reservoir? Does reservoir also affect Fourier expressivity? The answer is yes. We see that although the number of achievable frequencies is determined by the encoding, but it doesn't mean you will have non-zero Fourier coefficients. So here, by these numerics, we basically show that for some reservoir, you will get a lot of zero Fourier coefficient. Hence, the number of Fourier modes in the end you get is much smaller than the cardinality of capital omega. So in this chat, each row corresponds to a Pauli string measurement only applied on accessible qubits. So basically, we here take 3 examples from them. And each column corresponds to a reservoir. We detect here the identity reservoir or just low reservoir and the integrable Ising model and chaotic Ising model, as well as 3 Hadron reservoir. So we put 3 Hadron reservoir here is just to exclude some special cases. So the Ising model is defined as follows. You have the interaction term between labels in z direction, and also the energy in z direction for the integrable Ising model. For the chaotic regime, the parameter for the energy in x direction is non-zero. So basically, you can consider the chaotic regime as a Ising model with a arbitrary external field. And this paper basically considered the dynamics of the chaotic Ising model. Roughly speaking, this paper argues that if your time is enough long, then when you use chaotic Ising model, you can. So if the time is enough long, then the dynamics of chaotic Ising model will approximate the dynamics of Haar random reservoir. So yeah, back to the spectrum. We see that for the reservoirs with poor dynamics, you will have less non-zero Fourier coefficients. But for the reservoir with rich dynamics, almost all the Fourier coefficients are non-zero. Remember the previous chat just works as an example to better quantitatively study the effect of reservoir, which defines the richness of Fourier modes. So basically, this is the proportion of non-zero coefficients. And we take the average over all the Pauli strings. So now we plot the richness against the number of accessible qubits in semi-log scale. We see that the rich reservoirs, namely Haar random reservoir and chaotic Ising reservoir, will provide you a value close to 1. So basically for these two reservoir, you can expect you will get you can expect that all the Fourier coefficients are non-zero. But for reservoir with poor dynamics, the identity reservoir as well as integrable Ising model, they decay exponentially in system size. Remember that this 4 to the NA is exponential in system size. So basically we can, this curve implies that the number of non-zero coefficients for this two reservoir scales polynomially in system size. And this result actually suggests us to use chaotic Ising model and Haar random. But later we will see that Haar random will lead to concentration. As I mentioned earlier, the Fourier spectrum of a target is kind of related to the number of achievable frequencies. So in general, there are concepts. In general, there are two classes of algorithms for surrogation. The first class is equivalent simulation or full simulation of PQC. Namely, your surrogate model has namely, if you write down the prediction of your classical surrogate, you will get the same analytical form compared with the prediction of a quantum learning model. In cases that the achievable frequencies are exponentially many in system size, then there exists an efficient surrogate. Another class of surrogation is basically based on frequency sampling. So there are two important papers about this concept. The first one basically proposed the random Fourier feature method. It was initially proposed for classical machine learning, for classical kernel method. The idea is that although for some targets you have exponentially many frequencies, but in certain cases, you will only need to sample polynomially many frequencies. And with those, with the Fourier single mode determined by those sampling frequencies, you can approximate your target up to a very high accuracy. However, this method requires two conditions. First, the Fourier spectrum are expected to be concentrated, like this. And another issue is that so based on the training set, the RFF maybe provide you a better performance. They may provide you a lower training error, but it doesn't guarantee the same generalization ability of quantum model. So it may be perform worse on the test data because this random Fourier feature method will lose the inductive bias of quantum model. So yeah, in summary, if you want to achieve potential quantum advantage, you have to use untrivial encoding, such that you got exponentially many frequencies, and you also need to use some let's say untrivial reservoir, such that you have exponentially many Fourier you have exponentially many non-zero Fourier coefficients, and the Fourier spectrum is anti-concentrated. So in our work, we studied the Fourier spectrum of Haar random reservoir. Basically, we say that there's exponentially, so we say that for exponential encoding cases, the expectation value of Fourier coefficient is non-vanishing when the frequency grows. So basically, this tells us Haar random reservoir will provide anti-concentrated Fourier spectrum.
Sorry, actually, I have a question over here. How do you generate a Haar random reservoir, by the way? Like, do you kind of like just generate like Haar random metric and then apply that to? Yeah.
Okay. I think I should explain here. Sorry, I forgot to mention it. So in this chat, basically these three reservoirs are fixed, and we have the formula to calculate the coefficient. So these line plots are kind of deterministic. And here we generate the Haar random reservoir using the, so there's a function to generate Haar unitary in, I think it's available in many Python libraries. So for this, I remember we used the quantum optical one. It's called QTIP, I think. Yeah. So basically, you use the function. You will got a random Haar unitary.
And then you apply to your system. So it's just like generate some kind of. So over here, you are not really applying any gate per se, because like for the first three, you can, okay, for the first one, you didn't apply any gate because it's identity. For the second and the third one, basically you can decompose it in terms of the unitaries and apply it on like our quantum computing, but the Haar random one, you might not be able to do it unless you go and decompose it. Am I correct? Or like, do you have a way to decompose the Haar random unitary into gates? Yeah, maybe this is my question.
Do you mean, can I understand your question as like how to experimentally realize Haar random unitary?
Yeah, because like over here, you are doing it in terms of metrics, right?
Yeah.
Yeah.
Sorry, I don't know. But yeah.
Okay.
So basically, when we discuss the Haar random unitary, we also call it scrambler. So I think maybe there are some concept that can induce some chaos, but also preserve the, let's say, can induce some chaos, but the whole map is still not contractive.
Right. Like, because I know like for two designs, like you can do it on quantum computers, right? Just like randomly initialize for the parameters for like how way efficient and stuff. Like what if you use what if you use like two design unitary instead of the Haar random one? Would you expect the similar spectrum over here?
So if you want to achieve T design, if I remember correctly, I think if you use the random combination of Clifford gates, you will get three design.
Yeah. So for two design,
kind of way to.
So I'm just wondering, like, what if you only have two designs instead of like purely Haar random? Like what happened, what will happen to the spectrums? Yeah. So would it produce the same spectrums or?
I think it will be very similar.
It will be very similar.
Yeah, yeah. So my intuition is that if your unitary is sampled from hard random or we just say two design, then the probability that you have non-zero terms in your unitary will be very small. Obviously, the probability that you have some pattern like integrable Ising model or chaotic Ising model will be almost zero. So basically, you will always get such kind of spectrums.
Right. Okay. We actually have a questions over here, like why the first column, second row, the plot is empty.
Yeah, here?
Yeah, why it is empty?
Okay, maybe we go back to the formula. Yeah, so if we look at here, so if this is identity, right? Then basically this term will cancel. Oh no, sorry.
The reservoir is identity, right? So you still have observables over there, isn't it?
Yeah. So this is observable, and in the numerics we consider that it's separable. And note that the identity is also separable. So in the so the observable is a Pauli string on acceptable qubits, Tensor's identity on hidden qubits. So here for the hidden qubits, you can imagine that you will get 0, 0, the scalar multiplication between 0 and 0. And then for the acceptable space, if this is identity, it's just the I is bra J, a Pauli string, and cat I.
Yeah.
So for some Pauli string, you will get 0.
So when if, for example, Z basis, then you get 0. So like for that one,
exactly.
Oh, okay. So for that one, you just like consider different Pauli observables, and then you get to give you 0.
Yes.
Okay, I see.
Yeah. So basically that's why we in the end averaged this over all the Pauli strings to, let's say, to study the averaged performance of reservoir systems. Yeah. Okay. Yeah. Back to this chat. Basically, we from the numerics we show that a chaotic reservoir and hard random reservoir will provide you anti-concentrated spectrum. So namely, it tells you if you want to get some advantage, maybe you should consider these two reservoirs. Yeah, and for hard random, we also studied it analytically. But there's a fundamental limitation for QELM. Similar to quantum kernel case, it's the exponential concentration. Basically, for any Hermitian observable, its expectation value will concentrate exponentially in system size towards an input independent value. So we distinguish two types of exponential concentration. The first one is deterministic. Basically, the distance between your measurement outcome and this fixed point. Oh, remember that this O, we consider it as a function of input. So this distance is exponentially small in system size. The second one is the probability. Let's say for any positive deviation of the observable from this input independent fixed point, the probability that this is larger than this value is exponentially small. The consequence of exponential concentration is that, let's say if you have a fixed point, it's input independent, and your measurement outcome as a function of input fluctuates around this point. Then when we want to distinguish two different outcomes, you will need exponentially many shots to obtain enough accuracy in case that it's exponentially concentrated. So basically, this means that in practical, your QELM is just a input independent system and it's completely useless. And yeah, I want to remark that our this part work is can be considered as a extent of this paper studying the exponential concentration in quantum kernel methods. So here we identified 4 sources that will lead to exponential concentration. The expressivity of both encoding and reservoir unitary will lead to a probabilistic bound. The global measurement will also lead to a probabilistic bound. And the entanglement of the state before measurement, as well as the noise, will lead to a deterministic bound. So let's look into detail. So first, the higher expressivity induced concentration. So the probability. So here, after we take the excitation value over x, then this term becomes a input independent point. And we analytically show that the distance between the outcome and this point larger than a constant value, the probability for that is exponentially small. Basically, this bound contains 2 parts. The first part is scales exponentially in system size in the number of accessible qubits, and will towards 0 when NA is very large. The second part is a constant value, and it's determined by the expressivity of the encoding unitary. So basically, this diamond norm will provide you the distance between encoding unitary and the two design. For this, the numerics for this chat is based on a assumption of rotation of random Pauli rotations, random single rotations combined with C-dot gates, and we consider this set as 1 layer. Basically, if you increase the number of layers here, then the whole unitary will become closer and closer to the two design. And in this way, we use the depth of this unitary to control the expressivity of encoding unitary. You can say that if you increase the number of depths, or obviously you increase the expressivity, then the this lower bound or the value of saturation will be smaller. So yeah, for the reservoir expressivity induced concentration, the analytics is pretty similar to the previous source of concentration. It's still a diamond long, measures the distance between the reservoir unitary here and the two design. And the numerics is also basically follows the same setting.
Sorry, like for the previous one, like what reservoir do you use? Yeah.
Sorry?
Like for this encoding Hara expressivity induced concentration, what reservoir do you use?
Okay. I think in this case, sorry, I forgot it for a moment.
Let me go.
So for sure, we didn't use Hara random reservoir here. I think it's a Pauli system. It's a integrable spin system, or just identity reservoir for this case.
I see. Okay.
Yeah. So yeah, so basically, intuitively, the power unitary is directly after the encoding unitary. So the intuition is that if you have one layer of approximately 2 design unitaries, then you will get the concentration.
What if you have like, because like over here consider the encoding and reservoir like induced concentrations kind of separately, right? What if like you for the encoding and reservoir you halfway through and halfway through, like where do you still have concentration?
Sorry, can you repeat the last sentence?
As yeah, as in like because over here you just like have a term, like say your system size not that big, right? And then
Yeah.
it's like now what is this kind of like detect whether you have like the explicitly induced concentration is the distance, right? The reservoir,
Yes.
like
Yes.
between the reservoir unitaries and two designs. What if like now this term is kind of like not like your reservoir and the encoding unitary is halfway kind of like through the two designs, just like it's not exactly two designs. The combined effect will also lead you to a two design and exponential concentration, right?
Uh, so basically, the concentration in system size is so the variance will concentrate onto a kind of lower bound here,
Mm-hmm.
and this lower bound is this term.
Mm-hmm.
So let's say if it's a half two design,
Mm-hmm.
then probably you will get here or
Mm-hmm.
here or somewhere. But yeah, this diamond norm is, I mean, it's very difficult to analytically study the diamond norm.
Mm-hmm.
So I don't have any kind of good intuition like how to use this to share. Let's say how
Right.
to find this measure correspond to the half two design.
Right. I see. Okay.
Yeah. Okay. Let's move to another source of concentration, the entanglement induced concentration. So the analytical form is very similar to the entanglement induced baryon plateau. Here you also got a relative entropy, measures distance from reduced final state to the maximally mixed state, and for state rho k tilde that obeys volume loss scaling, this sum will concentrate exponentially in system size. But if it only follows area loss scaling, then this source will not provide you concentration. Yeah, and the third source is global measurement. For this, we assume that all the initial states, the reservoir, and the encoding unitaries are separable, because we want only the measurement part has the globality, and yeah, we exclude the entanglement from the reservoir and the expressivity from them. So we assume a global projective measurement applied on the final state. And then we found that the probabilistic upper bound scales exponentially in system size in both number of hidden qubits and the number of accessible qubits. So in the numerics, we show that it's a exponential scaling, and basically the profile is independent of the expressivity. The final source of concentration is the noise-induced concentration. In that case, we assumed air layer encoding with Pauli noise, and we define the noise parameter as the maximum of this prefactor. Then we obtain a deterministic bound. Basically, we show that the system output will concentrate exponentially in the depth of encoding. In practice, we can assume that the number of layers applied here is polynomially measured in system size. So basically, we also consider this as exponential concentration in system size. So let me now summarize our results. So basically, we discussed the expressivity and controllability as well as exponential concentration. So motivated by this, we did the Fourier decomposition, and we found that the encoding is crucial. They will fully determined by the Fourier frequencies. And the role of reservoir can be considered as a kind of source of inductive bias. Different reservoir will provide you different function bases, and based on this, you will get the prediction. So I want to emphasize that the Fourier expressivity is upbounded by the number of measurement. So basically, this tells you so basically, if you compare this with the classical case, this limitation tells you that you will not get some general quantum advantage if you use a quantum substrate, because you will always do the measurement in the end. So a bit outlook of this work. What we didn't discuss in details is the role of hidden qubits or NH. Basically, the effect of NH cannot be captured by the Fourier expressivity. So it's kind of weak hyperparameters. But we also expect that maybe if you increase NH, you can get a larger flexibility for the potential Fourier coefficients. Or if we extend to the quantum reservoir computing case, remember that all these accessible qubits are initialized after each step. So in this case, the hidden qubits work as a memory. So we expect that the NH will be much more important for quantum reservoir computing. It might determine let's say, affect the memory capacity, or indirectly affect the optimal length of time series you will use as input. So yeah, that's all of the results, and thank you for that.
Yeah, so thanks, Weijie, for the very interesting talk. And for the audience, if you have any questions, then feel free to unmute yourself, ask the question, or type the question in the chat. Then I could help ask the question. In the meantime, maybe I could ask a couple of questions over here. Like, because you are kind of like investigating the like trainabilities of quantum extreme learning models for machines, right?
Yeah.
So like there are different type of kind of like ways to induce the concentrations, like entanglement, noise induced, or like global measurements. And we know recently that macro like loss non-normal teams have kind of proposed some kind of unifying framework. Do you think those kind of unifying framework can be also applied here, and yeah, basically studies of this concentration altogether?
Yeah, I think it's very interesting to capture all these sources, like let's say, into a unique measure. So I heard about that. There are people study the so basically here we consider it's unitaries. There are I think the Marco has a ongoing project to like consider a channel and yeah, define the channel expressivity, etc. So I think it will be very interesting if we can unify all the sources into a unique measure. And also in the community of reservoir computing, in Ortega's paper, they somehow conclude that the contraction of the channel after each step is very important. So it's also interesting to see that if the sources can be viewed as a source of contraction.
Mhm. Right, I see. Yeah, another question that I have, that this one is kind of like open-ended, like because over here you are considering qubit, right? What happens if you kind of like consider qubit system instead? Yeah.
So actually at the very beginning, maybe not here, here. So here we actually consider the qubit case. So basically, if you consider qubit, it will not change the analytical framework, I think. And for the numerics, I guess you are interested in the concentration. So if it's qubit, let me find, here. Basically, this term is a dimension of the space, or this is the size of the matrix. If you use qubit, this is still the dimension.
Right. So
Yeah.
for qubit, like it will be concentrate mass faster.
Yeah.
Right, because the dimension of space, like even like same NA, for example,
Yeah.
then it's like much larger, so you'll be concentrate much faster over here. I see.
Yeah.
Okay. Okay. Yeah. So currently, I don't really have any other questions. Like how long does it take to does it take for you guys to generate a plot over here? Like to consider so many qubits have 14 qubits? Like how long does it take for you guys to do that?
You mean for the numerics?
Yeah, for the numerics, because it seems like 14 is quite large. And then
So
the circuitive is hold on, the circuitive is 1,000. So we have considered 1,000 layers and then 14 qubits. That one is huge, right?
yeah. So what we did is that we use a cluster, and the cluster has many cores. So basically here, so first for this plot, it's just analytically calculated from the equation for Fourier coefficients. But for these three plots, it's a sampling, and we run like 1,000 times or 500 times on the cluster. So we implement it in parallel. So basically, we run a single task for one shot on a core of the cluster. So and each task will take about 1 hour or 2 hours.
For like the extreme, like 14 qubits at 1,000 like dash. So that one will take like 1 hour per evaluation. Am I correct?
Yeah.
Okay.
I guess so. Yeah.
Okay, that's kind of reasonable to some extent.
Yeah.
Okay. Yeah, got it.
Yeah.
I see. Yeah, this is a very like nice work to combine everything that we know about and put it in the framework to study quantum machine learning. Yeah, actually, I'm more interested on this quantum resonant computing stuff, but it would be much harder to study, right? Yeah, the
Yes.
setting
Yeah.
is much more complicated, and yeah, the framework
Yeah.
might not be that nice compared to the quantum machine learning case.
Yeah. So basically, like in QRC, I mean, so the time series is in general not IID.
Right.
So
right. The
so
assumption is okay.
so the expressivity of this the expressivity of this will depend on the expressivity of this, or they are kind of correlated. So it's super annoying for QRC kids.
Yeah, when the identity assumption breaks down, then it complicates a lot of things.
Yeah, yeah.
Okay, I think now 5:03. Yeah, maybe you can end the seminar since like the audience doesn't have any
Yeah.
questions. So thanks again, Weijie, for the very detailed talk. And for more information, of course, we can refer to your papers to understand more about it. And yeah, thanks again, everyone, and see you guys next week. Bye bye.
Yeah. See you.
Yeah, see you.